All right, students, ready for a deep dive. Today we're looking at your BE 645 lecture notes on AI and radionics.
You've already got the textbook, so we're going beyond the basics.
We'll really be digging into how AI is impacting medical imaging.
Yeah, and it really all starts with feature extraction.
Feature extraction.
Think about it. You have a set of X-rays or CT scans or MRIs.
Wait, just pictures.
But there are patterns and details hidden in those images.
Uh-huh.
Those patterns can actually tell us a lot about what's going on inside the body.
So like we need some sort of key to unlock those secrets.
That's a great way to put it.
Uh-huh.
Feature extraction is that key.
Okay.
It's the process of turning those visual clues into data that AI algorithms can use.
So we're translating the images.
Exactly. We're taking the visual language of those medical images and turning it into a mathematical language.
The language of AI.
Right. So where do we begin with this translation?
Good question. Where do we start?
Well, the first step is to understand the radionics workflow.
Okay.
It's a 6-step process.
6.
It starts with acquiring the images.
Make sense?
Then we segment the regions of interest.
What does that mean?
It's like highlighting the important parts of the image.
Oh, so like if there's a tumor on a scan, we'd focus on that.
Exactly. We call those regions of interest your ROIs.
ROIs, got it.
And that sets the stage for steps 2 and 3.
Which are?
Feature extraction and preprocessing, and that's where the real magic happens.
So this is where we get down to business.
Exactly. This is where we use different techniques to analyze all the characteristics of the ROI.
The shape, the size, the texture.
Everything. And those pieces of information we extract are the features.
The features.
They're like clues to help us understand the image.
So we're like detectives at a crime scene, but instead of fingerprints, we're analyzing the texture of a tumor.
I like that analogy.
Uh-huh.
And one way to do this was by using handcrafted features.
Handcrafted.
Yeah, essentially they're mathematical formulas designed by experts to capture very specific information from those images.
Okay.
Think of it like a detective's toolkit.
With different tools for different jobs.
Exactly. You have first-order features, which are the most basic.
Like what?
Like analyzing the distribution of pixel brightness.
So just looking at how bright or dark the pixels are.
Pretty much. It's like looking at the overall color palette of a painting.
But that doesn't tell us that much, right?
Right. It gives us a very general idea.
We need more specialized tools to get the details.
And that's where second-order features come in.
Oh, okay.
These take into account how pixel intensities relate to their neighbors.
So instead of looking at individual pixels, we're looking at how they interact with each other.
Exactly. And that gives us information about patterns and textures.
Got it.
A powerful example of this is the gray level co-occurrence matrix.
That sounds complicated.
We call it GLCM for short.
Okay, GLCM.
Imagine you're looking at a pixel and its neighbor.
Okay.
GLCM analyzes how often different combinations of pixel brightness occur at specific distances and angles.
I think I'm starting to get it.
It's like analyzing the social dynamics of pixels.
Aha, the social lives of pixels.
Exactly. Seeing which pixels hang out with each other.
I like it.
And that can reveal a lot about a tumor's
Heterogeneity.
how much variation there is within the tumor.
Oh, I see.
So a tuner with a lot of different textures might be more aggressive than one that looks very uniform.
That makes sense.
And that's why it's so important to choose the right feature type for the job.
Like using the right tool for the job.
Exactly. So let's look at some real-world examples.
Okay, let's say we're trying to characterize a tumor.
Right.
How would we use these different features?
We'd start with those first-order features to get a basic understanding of the intensity distributions.
Okay.
But to understand its texture and how aggressive it might be, we'd need to use GLCM.
GLCM, right.
It's like using a magnifying glass to look at the tumor and then a microscope to zoom in on the texture.
So GLCM gives us that zoomed-in view.
Exactly. And there are even more specialized features like GLRLM and GLSGM.
What are those?
GLRLM analyzes runs of pixels.
Runs of pixels.
Like streaks of similar intensity.
Okay.
And GLSDM focuses on zones of similar intensity.
So like clusters of pixels that share a characteristic.
Precisely. We're analyzing the tumor from all different angles.
Wow, it's like having a whole arsenal of tools to analyze the tumor.
Exactly. And these handcrafted features are just the beginning.
There's more?
Oh yeah, there are even more advanced techniques.
Like what?
Well, one of the most exciting is local binary patterns, or LBP.
Okay, before we get into that,
Sure.
let's make sure we understand these handcrafted features.
Absolutely.
I think it would help to see how they're used in different medical imaging situations.
That's a great idea.
What about brain imaging?
Okay.
How do these features help diagnose conditions like multiple sclerosis or Alzheimer's disease?
Well, in brain imaging, we can use first-order features to look at the differences between white and gray matter.
Okay.
That can help spot abnormalities in the brain structure.
Uh-huh.
But to really understand what's going on, we need to look at the texture of the brain tissue.
And that's where GLCM comes in.
Right. And GLCM can help us see changes in white matter integrity,
White matter integrity.
which is crucial for diagnosing conditions like multiple sclerosis.
Right.
Exactly, where the protective covering of nerve fibers breaks down.
So it's like looking for cracks in the foundation of a building.
Exactly.
And what about GORLM?
GLRLM can assess directional patterns in white matter tracks.
Which are like the highways of the brain.
A perfect analogy.
Uh-huh.
Those patterns can be disrupted in conditions like Alzheimer's disease.
Because brain cells start to degenerate.
Right, so GLRLM is like checking for traffic jams on those brain highways.
Cool. And GLSZM?
GLSCM helps us understand large-scale lesion patterns.
Like in MS?
Exactly. Depending on the stage of MS, those lesions might be more confluent or scattered.
And GLSCM helps analyze those patterns.
Exactly. Each feature gives us a different piece of the puzzle.
And by putting those pieces together, we get a better understanding of what's happening in the brain.
And can make a more accurate diagnosis.
I see. Now, what about breast cancer imaging?
Oh, that's another important area where these features play a vital role.
I bet. How do they help us differentiate between benign and malignant tumors?
Okay, think of a benign tumor as a well-behaved guest and a malignant tumor as a party crasher.
Okay, haha.
We need to be able to tell them apart.
Right.
First-order features can help identify areas of high density.
Which could indicate cancerous tissue.
Yeah, it's like noticing a suspicious lump in a crowd.
Uh-huh. But we need more than that to know if it's really dangerous.
Right, that's where GLCM comes in.
GLCM again.
It can reveal irregular tumor margin.
Which means?
It means the tumor has jagged edges and sharp corners.
As opposed to smooth borders.
Exactly. A benign tumor usually has smooth, well-defined borders.
Okay, so it's like the difference between a round cookie cutter and a broken piece of glass.
Great analogy.
And what about GLRLM?
GLRLM can assess those directional patterns of fibrous tissues.
Which are often associated with tumor growth.
Right, it's like seeing how the party crasher is moving through the crowd.
Pushing and shoving its way in.
Exactly. And GLSZM gives us an idea of the overall heterogeneity of the tumor.
Right.
The more heterogeneous the tumor, the more likely it is to be malignant.
So it's like the party crasher is made up of all sorts of chaotic elements.
Exactly.
So we're not just identifying the tumor, we're analyzing its personality to determine the best course of action.
I like that.
These features are like giving us superpowers.
Haha, you could say that.
But you mentioned that these handcrafted features are just the beginning.
Right.
There's a whole other world of advanced techniques out there.
Exactly. And one technique in particular has really taken the world by storm.
Which one?
It's called local binary patterns, or LBP.
Okay, LBP, what's so special about that?
Well, imagine you're looking at a single pixel and its neighbors.
Back to the neighborhood analogy.
Right. LBP analyzes the neighborhood by comparing the brightness of the central pixel,
The one we're focusing on.
right, to the brightness of its neighbors.
So we're comparing the height of one house to the height of the houses surrounding it.
Exactly. If a neighboring pixel is brighter than the central pixel, it gets a 1.
And if it's darker,
It gets a 0. It's like we're creating a simple code based on brightness.
I see. So we're highlighting which houses are taller or shorter than the one in the middle?
Exactly. And by stringing those codes together, we get a unique pattern.
A fingerprint.
Exactly. A fingerprint that describes the texture in that neighborhood.
So we're looking at these relative brightness patterns instead of absolute brightness values.
You got it. And this approach is very robust to changes in lighting.
So it doesn't matter if the overall image is brighter or darker.
Right. Those patterns remain largely the same.
That's really useful for medical imaging.
It is. Lighting conditions can vary a lot between scans.
So it's like facial recognition for textures.
Exactly.
Wow. And what about computational efficiency?
LBP is very efficient.
Oh, good.
The calculations are pretty straightforward.
So it's faster than some of those other methods.
Much faster.
So it's fast, robust, and effective at capturing texture.
It is.
But how do we calculate those LBP codes for each pixel?
It's a step-by-step process.
Okay.
First, we choose a pixel and define its neighborhood.
The surrounding pixels.
Right. Usually it's a 3x3 square or a circular pattern.
Got it.
Then for each timer, we compare its intensity to the central pixel.
Brighter or darker.
Exactly. And we assign a 1 or 0.
So we're building a binary code.
Right. And then we arrange those binary values either clockwise or counterclockwise.
Like reading a compass.
You got it.
That's so cool.
And that becomes the LBP code for that pixel.
The fingerprint.
Exactly. And then we can create a histogram of all those
To
codes.
visualize the texture.
Exactly. The histogram tells us how often each pattern occurs.
Giving us a signature for the texture.
Precisely.
This is making so much more sense now. It's like going from a blurry picture to a high-resolution fingerprint analysis.
Great analogy.
But how do we actually implement LBP in a computer?
We can use kernels. Yeah, imagine a small matrix that slides across the image, performing that LBP calculation at each pixel.
Like a little robot analyzing each neighborhood?
Exactly.
And what about those edges where the kernel might go off the image?
We use something called padding to handle that.
Padding.
Don't worry too much about the coding details.
Okay.
The source material has scripts and examples you can look at later.
So we don't need to be coding experts to understand this.
No, not at all.
But seeing the code can help.
Right, it can solidify your understanding.
Okay, so let's see LBP in action.
Okay.
The source material mentions applying LBP to a 2D liver image. What did they find?
They looked at how the LBP image changes when you adjust the distance parameter.
The distance parameter.
Remember those pixel neighborhoods?
Yeah.
The distance parameter determines how far away those neighboring pixels are.
Oh, so a larger distance means we're looking at a wider neighborhood.
Exactly.
And what happened with the liver image?
As they increased the distance, the LBP image became less detailed.
It became smoother.
Right. The larger scale patterns started to emerge.
So it's like zooming out on a map.
Exactly. We get a tauter perspective.
So it's all about finding the right level of detail.
Right. We need to filter out the noise and focus on the important patterns.
So how do we choose the right distance?
It depends on what we're looking for.
Okay.
Are we looking for tiny details or large-scale structures?
So the question we're asking guides our choice.
Exactly.
This is so interesting.
It is.
It highlights how important it is to really understand LBP.
Right.
Not just how to use it, but why we're using it.
Absolutely. And how those parameters affect the results.
This is what makes radiomics and AI so exciting.
It is.
We have these amazing tools, and with careful consideration, we can unlock so many insights from medical images.
And those insights can really make a difference in people's lives.
It's really inspiring.
It is.
It's like we're using our brains to build tools that can see things our eyes can't.
And it's all to improve patient care.
Exactly. The insights we gain can help us detect diseases earlier.
Plan treatments more effectively.
And ultimately save lives.
That's the goal.
It's an incredible field.
It is.
I can't wait to see what the future holds.
Me neither.
This has been a fantastic deep dive.
It has.
I've learned so much, and I hope my student have too.
I hope so too. It's always great to talk about this stuff.
Well, on that note, I think it's time to wrap up this part of our deep dive.
Okay.
We'll pick up next time with even more about LVP and other advanced techniques.
Sounds good.
See you then.
See ya. So we were talking about the pros and cons of LBP, right?
Yeah, LBP seems pretty amazing.
It is. It's simple. It's efficient.
And it's robust to those lighting changes.
Exactly. And it's really flexible, too.
Right, we can tweak that distance parameter to focus on different scales.
And it has a compact feature representation, which is great for machine learning.
So what are the downsides?
Well, one limitation is that it can miss the bigger picture.
What do you mean?
It's really good at analyzing those local neighborhoods,
Uh-huh.
but it might not capture those larger patterns that span the whole image.
So it's like a detective, she's really focused on individual clues,
Right.
but might not see how they connect to the bigger crime.
Exactly. And it can also be sensitive to noise, like those random variations in the image,
Oh.
especially when we're using smaller distances.
Because those smaller distances are capturing those finer details.
Right, but those details might just be noise.
I see.
Another limitation is that fixed neighborhood geometry.
The circular square shape.
Right. That shape doesn't always fit the texture we're analyzing.
So it's like trying to fit a square peg in a round hole.
Exactly. And the way LBP represents texture can lose some spatial information.
How so?
It uses histograms, which tells us how often each pattern occurs.
Right.
But we lose information about how those patterns are arranged.
So it's like knowing the ingredients of a cake, but not the recipe.
That's a great analogy.
We lose the context.
Right. But even with those limitations, LBP is still really powerful.
It sounds like it.
And we can actually combine it with those traditional features.
Like GLCM.
Exactly. We can calculate GLCM from the LBP image.
So instead of looking at intensity relationships in the original image.
We're looking at how those LBP codes relate to each other.
Interesting. And what does that tell us?
Well, the GLCM features we get from both images can actually reveal different things.
It's like looking at the same object through two different lenses.
Exactly. For example, the energy feature tends to be higher in the GLCM calculated from the LBP image.
So LBP simplifies the texture, making it more uniform.
Exactly. And the contrast feature is usually amplified in the LBP GLCM.
Because LBP sharpens those intensity differences.
Right. And all those other GLCM features like homogeneity, entropy correlation, they all show interesting differences too.
Wow, so by combining LBP and GLCM, we get a much richer understanding.
It's like getting multiple expert opinions.
I like that.
And researchers have developed ways to address some of LBP's limitations.
Oh, really?
One of them is called Uniform LBP.
Uniform LBP. Okay.
The problem with regular LBP is that it can generate a lot of different patterns.
especially with larger distances.
Right.
And that makes the histogram more complex.
Exactly. So Uniform LBP focuses on patterns with at most 2 transitions between 0 and 1.
So it streamlines those patterns,
Exactly.
making the representation more compact.
And more robust to noise.
So it's particularly useful for noisy images.
It is, and the source material has examples of Uniform LBP applied to 2D images.
And it's effective.
Very effective.
This is incredible. We've gone from basic image analysis to these really sophisticated techniques.
And it's all thanks to the power of AI.
It's amazing how AI can help us understand and diagnose diseases.
It's really remarkable.
It's like we're using math and algorithms to unlock these hidden patterns.
It's like we're giving ourselves superpowers.
Haha, right, and it's all to improve patient care.
Exactly. These techniques can help us detect diseases earlier,
And plan better treatments.
ultimately leading to better outcomes for patients.
In a truly inspiring field.
It is, and I hope your students are feeling inspired too.
Me too. This is a field with so much potential.
And anyone who's passionate about using technology to make a difference can contribute.
Absolutely.
And remember that liver image we talked about? Let's go back to that for a
The
second.
one where they used LBP.
Right. Let's see what happens when we play around with that distance parameter.
Okay, back to the liver.
Remember how increasing the distance changes what we see?
It shifts our focus from fine details to those bigger patterns.
Exactly.
It's like adjusting the zoom on a camera, right?
Exactly. And the results for the liver image really show this.
How so?
With a small distance, like the LBP image is very detailed.
It picks up all those tiny variations?
Right.
But then what happens when we increase the distance?
When we go to 2 or 3 or 4, the image starts to smooth out.
Those fine details fade away.
Right. And the larger scale patterns become more prominent.
So it's like we're smoothing out the wrinkles to see the contours underneath.
That's a great way to put it. We filter out the noise and focus on what matters.
So how do we know what distance to use?
It depends on what we're looking for.
Okay.
Are we trying to find tiny microcalcifications, or are we looking at the overall shape of a tumor?
So the question guides our choice.
Exactly. Small distance for tiny details, larger distance for the big picture.
It's like choosing the right lens for a microscope.
Perfect analogy.
This really highlights how important it is to understand the nuances of LBP.
It does.
It's not just about knowing how to use it, but why we're using it.
And how those parameters can change the results.
This is what makes this whole field so exciting.
It is.
We have all these powerful tools, and we can use them to uncover incredible insights.
And those insights can help improve people's lives.
It's really inspiring.
It is. It's about going beyond what we can see with our own eyes.
Uncovering hidden patterns.
And using that knowledge to guide diagnosis and treatment.
This has been an amazing deep dive.
It has. I've really enjoyed it.
Me too. I've learned so much, and I hope my students have too.
I hope so too. It's always great to share this knowledge.
Well, on that note, I think it's time to wrap up our deep dive into AI and radionics.
Okay.
To all my students listening out there, this is just the beginning.
There's so much more to learn.
Keep exploring, keep asking questions, and keep pushing the boundaries.
The future of healthcare is in your hands.
It's been a pleasure diving into this with you.
The pleasure was all mine.
And to everyone listening, thanks for joining us. We'll see you next time.